Hey guys, this is chapter 1, part B. So we left off in the middle of the different indicators for global health and ecological health. We're going to go ahead and pick up right where we left off because I'm really bad at transitions and I don't really know how to start things. So here we go. One of the indicators is surface temperature and CO2 concentration. We looked at that in the previous slide, that big chart. Don't worry too much about memorizing each one of the little indicators like toads and frogs in the water and all that stuff. You will be very familiar with that by the end of the year because each one of those is like a chapter sometimes too, so don't worry about it too much. But in general, you need to know that when we look at surface temperature and CO2 and other types of greenhouse gases, we like to focus on CO2 quite a bit, but I just want to go ahead and drive this home right now. There are quite a few other greenhouse gases that we are worried about that do more than just raise the temperature. There are gases in the air that we really care about. Because of the different adverse health effects that they have, and also because we need a certain amount of these gases to have a survivable planet, have a habitable planet. But I do want to let you know, and let's go ahead and just get this one out of the way now, that a very important greenhouse gas that we have, chemical H20, just kidding, H2O, that's water. It is a greenhouse gas. If you've ever tried to boil a pot of water, you know that it takes quite a long time. And if you've ever gotten into like a pond or a pool when it's cold outside, usually it has kind of the opposite temperature extreme, right? It feels a little bit warmer if it's cold outside, or if it's hot outside, the water feels cold, right? That's because of water's very high specific heat. But I want you to go ahead and just file that away for right now because this is the most commonly missed greenhouse gas question. It's one of those all the following except sort of things, and water is in fact a greenhouse gas. All right, now we tend to look for anthropogenic greenhouse gases, and that is going to eliminate H2O because H2O is not created in overabundance because of anthropogenic or human activities, right? So what we're talking about usually is CO2 that was locked up in some sort of carbon sink. So you should be very familiar with that term by the time we get to it. So carbon sink. It's kind of like the idea of a heat sink, where if something's really hot, you put something there and it absorbs the heat so that it doesn't overheat your entire vehicle or something like that, or your electrical component. A carbon sink is very similar to that too. You takes the carbon and it stores it away for a very long period of time. So can you think of some things that would be carbon sinks? Think of some things that might breathe in carbon through cellular respiration and other life functions, right? So think about those things, and there's some really weird ones you would never guess, but we'll get to that later. I don't want to give away the whole year right now. But CO2 concentration and surface temperature is an indicator of ecological health. All right, here's a picture of that. I've already blabbered a whole lot, so I'm not going to get into this one too much, but in general, this is how that cycle works, right? Most of the heat that comes in from the sun is reflected back into space, but a certain percentage of it will get reflected and kind of refracted and bent around all over the place, re-emitted on the surface of Earth and get trapped in by this blanket that we have around ourselves, and those are our greenhouse gases. If we didn't have those greenhouse gases at all, we'd have something much more similar to Mars. Mars doesn't have a whole lot of CO2 in its atmosphere, and it's very little. I think it's 200 times less dense than the Earth's atmosphere, and so that leads to all kinds of problems, right? So it's not able to maintain a climate that is habitable by any highly complex life forms. So we do need this greenhouse gas. There is a fine balance. That's not to say what we're doing by unleashing stuff from carbon sinks for millions of years is helping, right? We were already doing plenty fine without all the stuff we're unlocking right now. Okay. Here's surface temperature and CO2 concentration. And of course, if you look at graphs like this that extend a little further out on the x-axis on either side, and you adjust the scale of the y-axis, this actually doesn't look this scary or anything. But it's worth noting that a scientist, especially climate scientists, or just a scientist in general, will look at little spikes like this, even though like on the original graph it may only look something like this. So I'm just going to draw like a very rough sketch of this same graph. So it might look something like, so you see there's something as simple as this little teeny blip right here, which is higher than this peak right here, might be what they went ahead and focused in on, right? So they might have taken this little part of the graph and focused on it and expanded it into this guy right here, into this whole thing that we're looking at here. That's not to say that the scientist is blowing things out of proportion, because I want you to think about something like this, right? If I have a sandwich, right, and the sandwich is 99.5% sandwich and only 0.5% dog poop, right? That all of a sudden, that little 0.5% becomes a very big 0.5%, right? So large percent changes don't always have little effects, right? So that's something to keep in mind. Sorry if that was a little bit of a crass comparison, but I think it works pretty well for our purposes. All right. So it's worth noting that we usually look over the past 100 years, usually from the start of the height of the Industrial Revolution is when we started taking climate data, and we also are able to reliably trace back CO2 emissions anthropogenic in nature. Okay, and we can talk about that later in the year, how we actually figure out, is this CO2 that's released from just natural causes, or is this something from human industry? All right, human population. So another indicator is the human population. Current human population is about 7.2 billion. You need to know that number cold and hard because it will show up on AP tests from time to time. They'll just straight up ask it. It's not a really hard fact to remember. Population scientists project the human population will reach 8.1 to 9.6 billion by 2050 and stabilize between 7.1 and 10.5 billion by 2100. And this right here, you should associate with the idea of carrying capacity, or K. So not this K, but K, the letter K, right? All right, so we're going to talk about that later and what it would actually take to sustain the human population. And we already know from our little lab that we did, our ecological footprint lab, that if the entire world consisted of Americans, we would vastly out-consume what the Earth could produce in a year. All right, key global environmental indicator 5, resource depletion. All right, we're talking about minerals and precious materials from the Earth. Coal, oil, and you already did like a little quiz over what's renewable and what's not. We know that these things are in the short term, and what I mean by short term is hundreds of thousands of years, we're not able to regenerate these, and it's not like I can take coal that I burnt and return it to back what it was without expending, unfathomable amounts of energy that wouldn't really make it worth it, right? Uranium, once we use that, it decays into other material that we really can't use to make fission reactions anymore. The other resources like aluminum and copper, they're finite but can be recycled. And the human population grows, it places greater demand on finite resources, right? That includes things like water, which is considered a renewable resource, but just because something is abundant and renewable doesn't mean it's abundant everywhere, right? So just keep that in mind too. Right? It's pretty crazy. All right, human development, the improvement of human well-being throughout economic advancement. And just remember that this right here, development could be good once human beings and societies reach a certain technological level and they can make better informed decisions about how they interact and manipulate the environment. But in the short term, as a country starts to develop and just start gaining affluency, which is just, affluency is just, if you don't know, just means more of this guy. Actually, this would probably be more appropriate, the green, right? Give me them greenbacks. But as we get more money, we talked about this in class today, societies will start buying more expendable technological goods that put a strain on the environment, right? Because it's, the novelty of it. All right, patterns of resource consumption. You need to know this graph. I'm not going to go over it too much. Just notice the difference between tan and green. Make sure you know what developed nations consume the most, like by which virtue they consume the most. So make sure you know that. And this is a really crazy fact right here. Only 20% of the world would be considered more of the higher developed, but we use up most of the world's resources. Human well-being depends on sustainable practice. What does sustainability mean? Living on Earth in ways that allow us to use resources without depriving future generations of those resources. So when we're studying environmental science, it's not really just about the whales and the snails. It's in saving them just as an ends in itself. Some people care about whales and snails. They just want them to live because, everything has feelings and everything has a purpose. But those things exist in a very, very fine house of cards that, without one, there's a cascading effect where, a lot of other things fall too. And eventually it gets to us. It's a ripple effect, right? And just remember that the ripple effect doesn't just end with the end of our lives, right? We don't just live solely for ourselves. The decisions we make now will have long-term effects in the future, right? So that's why we care about future generations. All right, so sustainable development, this is something very important, and it's very interesting to watch places like China and India that are going through like a medium development phase into like something that more resembles what we had maybe 50, 60 years ago. And, there was a lot of fear that with that affluency, since they have 3 times our population, are going to consume so much more. But you're starting to see that places like China are outpacing us in terms of solar panel development and solar technology, carbon capturing, recapturing. So that's interesting, right? So there is a way to get through the growing pains of dirty industrialism, right? Sustainable practices. Environmental systems must not be damaged beyond their ability to recover. And you're going to see that a lot when we get into resource mining and laws that we have to to reclaim land that's been used for human industry and capitalism, right? Renewable resources must not be depleted faster than they can regenerate. So I want you to think about some resources that we use up that will probably be gone, eventually, right? Does it make sense to come up with a contingency plan as we're running out, or does it make sense to always be developing newer, cleaner technologies that can make us more energy independent and whatnot? I might have given away what I was talking about by saying energy independent. Okay. Non-renewable resources must be used sparingly. And we have to have this idea of biophilia, which means love of life. Life, philia, love. All right, so check this out. This is very, very important. Our ecological footprint, you did an ecological footprint, and probably the thing that you noticed took up the most of our footprint had to do with the amount of land we take up, right? But that land we take up is not literally just habitation, like settlements and things like that, but it also comes from how we derive our energy, right? If we are expending fossil fuels to do that, we had to get the energy from somewhere, right? It probably had to do with land clearing. I mean, it's all just like a ripple effect. Whenever we do something, we have to change the environment, right? So land area is usually how we figured this out. Different types of foods that we consume, especially meats, take up so much more energy to raise than just plants do. And of course, seafood. If you get really nice sushi from all over the place, guess what? It has to travel from very far away. So this is a very useful picture to have, and I would probably add this to your notes in some way. All right. Okay, now we're going to get into some of the drier stuff, but this is going to be the stuff of how we investigate ideas this year and how we investigate new materials. So we're going to look at the scientific method. And as we go further into the year, we'll talk about FRQ questions on the AP exam and how it relates to this specific section of the notes here. There are a few things you need to include in every FRQ answer that asks you to design a lab, because there will be a design a lab question from time to time. Hey, you know about the scientific method. I'm really not even going to read this. All right. Now, one really important thing that I like to focus on as a teacher is not really coming up with a hypothesis first. So I kind of like how this PowerPoint doesn't put the hypothesis in the first place, because if you're anything like I was when I was a kid, I'm trying to make sure that I do the lab correctly and I don't mess up. So I kind of want to know the answer up front, right? Otherwise, I end up making like a hypothesis about how aliens are purple and they like to eat peanuts. And then I do a lab about projectiles, and I have to go back and change my hypothesis at the end. And I don't like that feeling very much, so I usually like to start with observations and questions. And observations are usually data, right? Lots of data. So we look at data, we form patterns. My friend Pat took a turn. And we look at patterns and stuff like that, and then we come up with some sort of claim, right? And then, we test the validity of that claim, we argue, we make arguments against it, we try to test it that way, right? And I think that's a little bit better. In general, though, like this is kind of like the old school way that the scientific method goes, but just know that you can really start the scientific method in really any order. Sometimes people discover stuff not looking for it, right? So they're doing some other lab, like maybe looking for the amount of lead in some sort of cubic zirconium as it decays, and then they end up realizing that there's lead all over the place, and they find out lead poisoning is bad, and there's no safe level of lead. So this is actually a true story. But that's what I mean, though, is like you don't always set out to test some sort of hypothesis that just popped into your head. You know, sometimes it's the result of data collection from some other experiment, right? And we're going to talk about our FRQ. You always need to form a hypothesis for your FRQ or some sort of testable prediction. And then you need to describe the type of data collection, the lab equipment you're going to use. And you're also going to talk about how your results will be valid during the interpretation, how to know that they would be valid results, right? And you have to define some sort of control, you know, so all this stuff at the front. All right, here's a hypothesis. A null hypothesis is just saying something that's obviously wrong. All right, so like in any good FRQ, you would want to talk about ways that would make your data valid and make your experiment valid. So you talk about replication, just simply saying I would redo this again or have somebody else peer review it, blind test it to check the validity of it, make sure that the same outcome would happen again. You want to make sure that your sample size is appropriate. You know, if you're testing out the effect of milk on beetles, you know, you don't just want to get one type of beetle that has some sort of weird abnormality, like it only has one wing and you only tested milk on one-winged beetles. You know, you want to control for stuff like that, right? So defining control, like maybe having a beetle that isn't exposed to milk at all, right? If that makes any sense. So all these things here go into the validity of if your experiment was carried out correctly and if the outcome is true, right? How truly it can be taken. Or, you know, you've seen the old bullseye things with accuracy and precision. And then there's always a little bit of uncertainty, and quantifying that uncertainty in your result, talking about what weaknesses you might have had is a good thing. So that way others can see it and maybe improve upon it. All right, here's that picture. So once the results have been obtained, analysis of the data begins. Two types of reasoning, inductive and deductive. Inductive is the process of making general statements from specific facts or examples. So you're looking at it and maybe continuing a pattern or something. Deductive reasoning is applying a general statement to specific facts or situations. Okay? Scientists maintain multiple working hypotheses, even within the same experiment sometimes. Scientists reject or accept a hypothesis based on what the data show and begin to generate conclusions based on their results. All right, now we're going to get into like these differences between everyday scientific words and the actual use of scientific words. So when scientists publish papers in conferences, they publish the results of their investigations. This allows other scientists to repeat. So this is the idea of replication and repetition. They verify or challenge the results. This can lead to a hypothesis eventually becoming a theory. Now this is where we get into kind of murky water, because when somebody says that's just your theory, right? They mean like you're just guessing, right? But in science, a theory has gone through this entire step that we just talked about. It's gone through the scientific method. It's been peer-reviewed. It's been challenged. It's been validated after being challenged, right? A lot of the times people that don't think your findings are true or valid, they test it themselves, right? And they use the exact same steps that they might change something, but they note those changes. And even then, you know, something like the theory of gravity still holds. And just remember, that's pretty crazy, right? The way we use the word theory as just kind of being like, it's whatever. Like, I don't think you really know what you're talking about. That word theory is applied to the word gravity, right? It is a precursor to the word gravity, the theory of gravity. And you wouldn't say to somebody that says, definitely don't try jumping off that table and landing on your head because there's gravity. You would never tell them, oh, well, that's just a theory. You know, I think that's just your opinion, man. Like, so I wouldn't do that, right? So that's the difference between our everyday use of the word theory and the scientific use of the word theory. All right, so control group has the exact same conditions as the experimental group except for one single variable under study. So you don't want to have too many variables happening at the same time. So I like to think of a control group as just like normal situation, right? Or if I'm looking at milk, like I said before, like if you're putting milk on beetles, you just have a group of beetles that doesn't have milk on them and see how they would grow and react. That way you can test to see, you have a baseline of comparison. All right, so go through this right here. Go ahead and read that. I'm not going to read that to you. You can pause that. I'm pretty sure you can find something like this in your textbook anyways. But notice here how they are very methodical in the way that the experiment was carried out. Say they have some sort of question. We're obviously not going to be doing stuff to living animals in terms of, hurting them and things like that. We'll be messing up the plants a lot, like radishes and bean seeds and things like that. Plants don't have feelings, I don't know. Well, if they do, we're doing really horrible things to them, right? Alright. Okay, home front now, here we go. Home stretch. Natural experiment, instead of being in a lab, you're outside. So you might be able to do a lab out in nature in some part of the forest, right? So that's just a possibility that you also have in the realm of environmental science, so just keep that in mind. And environmental science presents unique challenges. There is no control planet, so we don't know how Earth would have been without humans or anything like that currently, right? Like the best we can do is maybe go somewhere without human interaction and manipulation, but keep in mind that the atmosphere Earth goes everywhere, right? So it's impossible to find somewhere above ground that isn't like an ice core or something like that that isn't affected by CO2 output for the last 150 years, even if it's a remote region of the world, right? Everything's getting affected little by little. It's difficult to determine what is better or worse for the environment, just because everything affects everything. And we have to live here. I mean, the option isn't let's just get rid of humans and let's stop existing. So we have to sometimes make these weird, dicey decisions and on how we interact with the environment and what stays and what goes. Environmental science has so many interacting parts, it's not easy to apply one system to another. Between the water cycle and nutrient cycles, atmospheric cycles, we have biological cycles, you have human geography, and all that stuff kind of messes things up, right? And it's really hard to study one thing and have a control separated from everything else. And also, when people are unable to meet their basic needs, they're less likely to be interested in protecting the environment. Like, think about how uninterested you would be to save snow leopards if you lived in snowed leopard land and they were having some sort of civil war or some sort of alien invasion, right? Like, all of a sudden you're worried about, are you going to be able to watch the next season of Game of Thrones, let alone, that's important. You're not thinking about saving some sort of snow leopard, right? So that's just what happens to people, and it's easy for us to judge other cultures when, they're doing things like eating snow leopards, but, it's much harder to probably live those lives in those circumstances. So you'll see as we go through the year that increasing the standard of living for people around the world, increasing education for all human beings within our society, and not just a certain group or class, making sure that human rights are at the forefront of what we care about, go hand in hand with economic and environmental concerns, right? So that's my lofty ending to this entire chapter. Hope that was helpful. Bye.